Previously, I have provided videos on Hamilton Jacobi theory, and I hope you have definitely watched all my videos on this SJ theory, and after that, you have learned how this SJ theory can be applied to solve a physical problem. In fact, you know that this nature is full of vibrations, or you can say periodic motions and vibratory motions. And so this periodic motion is of special interest in many physical systems. In your lower classes, definitely you have studied waves and oscillations, where we talked about the periodic motion. The motion of a planet, motion of a satellite, all are examples of the periodic motion. And from the very beginning, among the physicists, this periodic motion is of a special interest. So definitely there should be a strong mathematical tool to discuss the problems of periodic motion. In fact, this Hamilton Jacobi theory, which you have studied earlier through my videos, actually this SJ theory provides a very powerful method, powerful tool to study the problems in periodic motions. And therefore, how we can apply this SJ method or the Hamilton Jacobi concept to handle the problem of periodic motion. Now our present aim is to see that very fact. Okay? Actually, when you will try to solve the motion of periodic motion on the basis of Hamilton Jacobi theory, then you will see later on that in Hamilton Jacobi theory, where there is the base Q and P, that is generalized momenta and generalized coordinate and generalized momenta. Actually, if your aim is to apply the SJ theory to discuss the problem of periodic motion, then it is more convenient to change this basis Q and P to new basis J omega. Here, this quantity J is known as action variable, or it is also called phase integral. Why it is called phase integral, we will see later on. And the another variable, omega, which is used as the base, that is called angle variable. Actually, in this lecture, we are going to see how we can define this action variable and the angle variable, and how the basic problem of periodic motion can be solved by using this. In fact, you know, basically when we solve a problem of periodic motion, our prime aim is to find the frequency of the motion without knowing the details of the orbit, details of the trajectory. So how in general, when our system has a large number of degree of freedom, then how we can use the idea of these two variables, that is action and angle variable, to find the frequency of a periodic motion. Our aim is to discuss in general in this particular lecture. But after getting ideas how to find the frequency of periodic motion in terms of the idea of action and angle variable, later on we will see particular problems. For example, we will deal the problem, Kepler's problem, okay, in action angle variable, and discuss how this problem can be handled in terms of it. Okay. So as I have told you that this Hamilton Jacobi theory actually provides a very powerful tool to study the problems of periodic motion, and in this technique actually the basis QP are transformed to the basis j omega, where I have told you that j is the action variable, which is also called phase integral, and omega is called the angle variable. Why these are called action and angle variable, we will see later on. Okay. In fact, when you have studied the H theory, then we have seen actually that we choose alpha k as new momenta. Okay. But in this technique, we do not choose alpha k as new momenta. But instead of this alpha k, here we use suitably defined constant jk, which form a set of n independent function of alpha k. It means this jk is defined as the quantity which are actually functions of alpha 1, alpha 2, so on alpha. Okay. Now, basically, when we discuss the periodic motion, like motion of a planet, all planets move under the gravity of the sun, and gravitational force, is a conservative force. So, more or less, we always encountered conservative system when we talk about the periodic motion. So, let us limit our discussion here to a conservative system. So, I have considered a conservative system, and if the system is conservative, then the Hamiltonian of the system will not contain time explicitly. It means Hamiltonian of a conservative system is not an explicit function of time, and therefore if you want to write the HJ equation, Hamilton Jacobi equation, for such a conservative system, what will be that? You can remember, if you have not watched my video on HJ theory, you must watch the video on HJ theory before watching this. Okay? Only then you can understand it. So, HJ equation for a conservative system for which the Hamiltonian is not an explicit function of time can be written in this manner. H of q1, q2, so on, qn, these are generalized coordinates, Del w by del q1 plus partial derivative of del with respect to q2, so on, partial derivative of w with respect to qn, and that is equal to alpha 1. In fact, here, w is what? W is the Hamilton's characteristic function. Okay? W is called Hamilton's characteristic function. Okay? Actually, in this equation, the variables q1, q2, so on, q3, which are actually generalized coordinates. In general, you may call these variables by the symbol qk. These variables qk occurring in this equation 1 are actually separable. But these are separable only when the solution of this equation 1 will be of this form. W equal to W of q1, q2, so on, qn, and semicolon alpha 1, alpha 2, so on, alpha. Or you can also write in this manner, this is summation over k wk of qk, alpha 1, alpha 2, so on, alpha. Actually, this W splits this equation 1 into n equations, and for each value of q, we have a particular Hamiltonian, okay, and particular constant alpha. And these n equations will be given by hk of qk, del wk by del qk, alpha 1, alpha 2, so on, alpha, and this is equal to alpha k. Actually, here this k runs from 1 to n. So when you take k equal to 1, then this equation will become h1 q1 del w1 by del q1 alpha 1 alpha 2 so on alpha. After that you may take k equal to 2, then equation will be h2 of q2 comma del w2 by del q2 alpha 1 alpha 2 so on alpha n equal to alpha 2. So each of these equation 3 involves only one of the coordinate qk, either q1 or q2 or q3 and so on. Okay? And the corresponding partial derivative of wk with respect to qk. As I have told you, when you will take k equal to 1, then the partial derivative will be also del w1 by del q1. Okay? Now, actually, in this condition, the equation of canonical transformation will have this form pk. This is generalized momenta, you know. This is given as del wk by del qk. And when this equation is solved for pk, then it is found that this pk is equal to pk of qk comma alpha 1 alpha 2 so on alpha n. Okay. In fact, this equation number 5 represents actually the equation of orbit. Okay. And in fact, this equation represents the orbit equation of the projection of the representative point, or the representative point means phase point of the system on the plane qk comma pk in the phase space. Okay. In fact, if for all the values of qk and pk, the orbit equations represent either closed orbits or the periodic functions of qk, then we can define action angle variable for the system. Now, how we can define action variable? Now let us see. In fact, this action variable, which is also called phase integral, this is defined conjugate to the coordinate qk by this integral. Jk equal to integral for a complete cycle of qk pk dqk. Okay? Pk dqk. This is actually the basic definition. Here this integral is carried for a complete period. Okay? So I have mentioned it here, you can see the integration is carried over a complete period of oscillation or rotation cycle of qk. Okay? Now if you consider that qk's are cyclic coordinates, you know, if qk's are cyclic coordinates, okay, then I have provided a complete video on cyclic coordinate in this playlist earlier. You can watch that video and you will find there that actually if qk are the cyclic coordinate, then its conjugate coordinate or conjugate momenta are constant. Okay? So if you treat that qk are the cyclic coordinate, then this pk will be constant, and therefore this pk can be taken out from the integral sign. And in that condition, if you will find the integration of dqk for a complete cycle, that is between 0 to 2 pi, then this action variable jk is given as pk times integral 0 to 2 pi dqk. And this integral will be equal to 2 pi. Therefore, when qk are actually the cyclic coordinates, then action variable jk is simply given by 2 pi times pk. Okay? Now we will make use of equation 4 in equation 6. Let us see here. This is your equation 4. where Pk is defined in this manner. This is del Wk by del Qk. Okay, and let us use this equation 4 in 6. Here at the place of Pk we will write del Wk by del Qk. Okay, del Wk by del Qk. And therefore Jk will be equal to del Wk by del Qk dQk. Okay. Now, since Qk is a variable with respect to which here integration is done, and you know, as it is a definite integral, so after integration, in the final result, there will be no Qk, because, for example, if you integrate, let us say x dx, and the limits are 0 and 2, this will be x square by 2 and limits are 2, 0. So this will be 4 by 2 minus 0. Is x present here? Answer is no. Similarly, you can say, since the Qk is a variable of integration and therefore and the integration is a definite integral, so this Qk will be out when integration is over. Okay, so you can say that actually this Jk will be then only a function of alpha 1, alpha 2, alpha 3, so on alpha n, not of Qk. Okay, have you understand? So Jk is a function, and this is actually a function of n constants alpha k, that is Jk equal to Jk of alpha 1 comma alpha 2 comma so on comma alpha. Okay, actually this equation is just a transformation equation. If you know alpha 1, alpha 2, so on alpha n, you can find Jk. Okay, but the inverse transformation is also possible. You may solve this equation 9 for getting the value of alpha in terms of j. Okay, so when this equation will be solved for different values of alpha, then we will find that alpha k is equal to alpha k of j1 comma j2 comma so on comma jn. Okay, now you know, in this condition our Hamilton's characteristic function will be a function of q1 q2 so on qn and j1 j2 so on jn, and this may be written as summation over k wk qk comma j1 j2 so on jn. Okay, but you know, in Hamilton Jacobi theory this h is equal to alpha 1, and alpha 1, you know, from here this equation number 10, this alpha 1 is a function of j1 j2 so on jn. Therefore you can say that this h is actually a function of j1 j2 so on jn. Okay, so this is all about the action variable. Now we will talk about the angle variable. Okay, as I have told you that the action variable Jk is the conjugate of Qk. Okay, just like that, the conjugate coordinate to this Jk, that is conjugate coordinate to the action variable, is called angle variable. Okay, so I have mentioned here the generalized coordinate conjugate to Jk are called angle variables omega k, and this is in accordance with the canonical transformation. You know, if omega k is the conjugate coordinate of Jk and w is actually the Hamilton's characteristic function, then this omega k is given by del w by del jk. Or you may write this expression in this manner: summation over L, where L runs from 1 to n, del omega L by del jk ql comma j1 j2 so on jn. Okay, you may write like this. Now, since jk has the dimension of angular momentum, so the coordinate conjugate to it must have the dimensions of angle. Okay, or you can say this must have, these are definitely dimensionless, and that's why this is called angle variable. Okay, so this is the basic way by which you can define this angle variable. But now, how we can write the equation of motion in terms of these two new variables? You can see, when you write the canonical equations of motion, that is the Hamilton's equation of motion, when your base is Qp, then our first equation of motion is Qk dot equal to del H by del Pk. Okay, and Pk dot, this is equal to minus del H by del Qk. These are Hamilton's equations. Here in fact, this jk is the coordinate used for P in this new formulation, and omega is the coordinate used for Q. Okay, because this basis Qp has been transformed to omega j. Okay, again, actually in this case, the Hamiltonian will not change, because the Hamiltonian contains the action variable. Moreover, the generating function W is time independent. So the new and old Hamiltonian are also same, and that's why in this case you can write the Hamilton's equation of motion in this manner: jk dot equal to minus del H by del omega k. This is just analogous to this equation. And omega k dot is equal to del H by del jk. Okay? But as you have seen earlier, that this H is a function of jk only. It means H does not depend on omega k explicitly, and therefore this partial derivative of H with respect to omega will be 0. That's why I have written here jk dot equal to minus del H by del omega k, and that is equal to 0. But as jk dot is 0, it means djk by dt is 0. That means jk is constant. Jk is constant. So from this first Hamilton's equation, we obtain this result that jk equal to constant. Now let us see the second equation: omega k dot equal to del H by del jk. Okay? Del H by del jk. And this will be actually a constant. Okay? And that constant is represented by the symbol nu k. And this nu k is just function of j1, j2, so on, jn. Now, omega k dot is simply written as d omega k by dt, that will be equal to nu k. You will see later on that this nu k has dimensions of frequency, and therefore from here you can find the value of omega k by integrating it. Integral of d omega k equal to nu k integral of dt. So omega k is equal to nu k times t plus beta k. Actually here beta k is integration constant. Okay. Actually in this equation 15, all these new k's are identified as frequencies of the periodic motion. Okay. In fact, the advantage of action angle variable method is that the frequency of the periodic motion you can obtain without dealing the complete solution of the problem. In this manner, we can easily obtain the frequency of oscillation, which is actually the basic problem of any periodic motion. Okay. Now, let us consider that the change in angle variable omega k with a completion of one cycle by this QL. Okay. One of the, when you write QL, this is one of the coordinates. Okay. And that change we denote by the symbol delta L omega k. Here I have actually written a subscript in the symbol delta. Actually this index L on delta indicates that only QL is changed. Only QL, not Q1, not Q2, not QL plus 1, QL plus 2, QL minus 1. Those are not changing. Only QL changes. Okay? And that will be equal to what? That will be equal to integral for a complete cycle del omega k by del QL times dQL. You can write this. But you have seen that this omega k is equal to del W by del Jk. So let us replace this omega k here in above equation by del W by del Jk. And so this delta L omega k is equal to integral over the complete cycle del 2 W by del QL del Jk del QL. Now, since integration is with respect to QL, so you may take this operator outside of the integral, del Jk, integral del W by del QL dQL. And this del W by del QL, you know, you have seen, this is nothing, this is simply PL. Okay? This is PL. And integral of PL dq for a complete cycle. What is this? This is action variable. We have learned earlier that Jk is defined as integral for a complete cycle Pk dqk. You have seen or not? Definitely you have seen. On the basis of this definition, you can write the integral of PL dql for a complete cycle is equal to JL. So instead of this, I have written here JL. So delta L omega k is equal to del JL by del JK. But what is this del JL by del JK? You know, this is Kronecker delta LK. This is just definition of the Kronecker delta. Del xi by del xj. This is delta ij. This is definition of Kronecker delta. So delta Lk here is Kronecker delta. And you know, this Kronecker delta is equal to 1 when L will be equal to k. But it will be 0 for L not equal to k. Therefore, you can say that delta k omega k, this will be 1 when L is equal to k. But delta L omega k, this will be 0 if L is not equal to k. Okay? So in fact, this result shows that only when Qk goes through a complete period, omega k changes by unity. That will change by unity. This will be 1. Only when this Qk will go a complete cycle. Then. And therefore, this equation, you can see, omega k equal to nu k t plus beta k. If you will find the change in omega k, since nu k and beta k are constant, so change in omega k will be equal to nu k times change in t. So delta k omega k equal to nu k times delta t. This is change in t. Now for a complete cycle, this time interval delta tk is denoted by the symbol tau k, and this is called period of the motion or time period of the motion. Okay? And you have seen for a complete cycle, this change delta k omega k is equal to 1. You have just seen here. So this delta k omega k equal to 1. Now let us substitute these two values in this result, and then you will see that 1 is equal to nu k times tau k, and therefore nu k is equal to 1 over tau k. This is obvious. If tau k, is the time period of this periodic motion, and nu k is its frequency, this frequency is just the reciprocal of the time period. This is a well-known result. So in this way, without finding the details of the orbit of the particle or system describing this periodic motion, we can obtain the frequency of this periodic motion, okay, without going into deep into the this problem of this periodic motion. Okay, so this is the usefulness of action angle variable concept. But this is just a theoretical aspect. In the forthcoming lecture, I will talk about a very important problem, and that is called Kepler's problem in action angle variable. Okay, then how this concept is applied to solve the problem of periodic motion, that will be very clear to you. Okay, thank you very much.